vehicles, or UAVs, continue to play an increasing role in homeland security, military operations, and civilian sector applications. Used primarily for surveillance and target acquisition, these vehicles have significant mobility advantages. With the exception of UAVs with weapons payloads, the vast majority typically try to avoid contact with the ground rather than interact with it. The aim of this research is to develop a mobile manipulated unmanned area vehicle, or MMUAV, that goes beyond simple pick and place. This artist's conception shows a futuristic area vehicle with multiple dexterous arms. A prototype vehicle was constructed using an off-the-shelf quad rotor. These types of rotorcraft are simple, have strong hover control, and good payload-to-weight ratios. The drawback of the quad rotor is a tendency to drift due to the inherent instability of the rotorcraft from its motors and rotors. To compensate for variations in roll and pitch during flight and manipulation, a buoyancy envelope was attached to the quad rotor to provide restoring forces and an increased moment of inertia for the vehicle. By analyzing test runs with and without the buoyancy envelope, we have verified that the hybrid structure does improve flight stability. Experiments show that the prototype vehicle is capable of both flight and actuation. The prototype proved to be very difficult to control manually, even with the buoyancy envelope. In this test scenario, human operators are controlling both the quad rotor and manipulator arms. With the arms fully extended, the aircraft instability prevents object manipulation. Therefore, we implemented computer-aided control using a motion capture system. The vehicle is seen here interacting with a target object with all three manipulator arms. A closed-loop controller compensates for disturbances caused by changing centers of gravity during arm actuation and contact with the target. The importance of these experiments is to characterize the forces and torques generated from both arm articulation and reaction forces during target manipulation. Initial results are promising, and the prototype vehicle has proven to be an important milestone for current and future work. From the lessons learned of our prototype vehicle, we have also built a miniature gantry test rig to emulate the pose of the UAV and perform mobile manipulation in a controllable and repeatable manner. Based on Drexel's Systems Integrated Sensors Test Rig, or SISTER, the flight emulator uses model reference adaptive control to eliminate error between the gantry state and the flight dynamics model of the aircraft. Due to the difficulties of using multiple manipulators and end effectors on an aircraft, a hybrid impedance control strategy was implemented. The use of force feedback and impedance control is a well-practiced approach for manipulation and provides an interesting advantage for the aerial manipulation problem. The sense forces can be communicated to the rotorcraft stability controller to provide overall stability. Future work will include larger and more dexterous manipulators with an aerial platform capable of greater payloads.
Questions?
Yes.
So how do you foresee a single operator controlling both the grasper and the aerial vehicle?
Right now we have two operators, one for the quad rotor itself and one for the manipulator. So the goal is to put an autopilot on the actual vehicle to take care of really all of the low level control. And then we're also using a motion capture system for basically high level position control. So that can with that system we can eliminate that operator, but it's not we're not tied to motion capture. And then of course the end state or the future work would be to implement feedback in the prototype vehicle that we have, and to try and do basically autonomous grasping and manipulation. So everything in the video with the actual flight is all teleop minus the position control provided by motion capture volume.
Yeah.
Crap.
Don't you generally want to raise the center of mass of the helicopter in order to increase pitch agility? I'm just curious as to the reasoning behind effectively lowering it by putting a balloon on top.
Sure. Well, so of course the balloon itself is increasing our moment of inertia. Sure. Is it shifting the center of mass? I mean, the balloon envelope is and the linkages are not that heavy. So of course by having that large radius really in effect does help to restore any pitching and yaw motion or pitching and roll motions.
There you go. Thank you very much.